So as we are looking at this stuff, we are going to be dealing with our central limit theorem again, and our confidence intervals and hypothesis testing from our standard normal distribution curve. So the central limit theorem basically says that our distribution of our sample statistics for our mean or our proportion is normally distributed. And yes, it's going to be normally distributed if the sample size is large enough. So as we review here, a lot of the stuff we've been dealing with all have this bell-shaped curve from what we've noticed, which is our normal distribution. So the central limit theorem holds true with the original distribution being sufficiently large enough sample size. Now, if it's more skewed, you need to have a larger sample size for the central limit theorem to work. Basically, though, if you're dealing with quantitative data, if you have a sample size of 30 or above, that's normally sufficient, unless it's very skewed. If you're dealing with categorical data, you want to have at least a count of 10 in each category for it to end up being normal. So let's go ahead and look at the hearing loss stuff again. We have 1,771 Americans between 12 and 19 years of age, and 19.5% had some hearing loss. Is this a dramatic change from a decade ago? Well, let's go ahead and do a 95% confidence interval for those that may have lost some hearing. So we could go and do this on StatKey. We could enter in our proportion. We could do confidence interval, which is the center column, do a proportion. Now you might be wondering, where does this come from for 345? Well, if you go back here, if you take 19% of how many we had here, that's where that comes from. So if you take 0.195 times 1,771, that's where you get this number. And it gives us our proportion. Then we could do a two-tail, and we could do our 95% confidence interval, and we have that down here at the bottom with these two things. So here's our interval. Once again, it looks like a normal curve, so we should be able to approach it from a normal curve also. So if we have our bootstrap distribution, we could do the middle, whatever percent level we wanted, and we could do that looking at it approximately with a normal distribution with our statistic that we got from our sample and our standard error. So looking at this, we could do our statistic with our normal curve. Our statistic is up here. Our standard error is right here. So we could do a normal distribution with this being our mean and our statistic being this. On StatKey then, we could go ahead and type in underneath normal distribution at the bottom on StatKey, hit our edit parameters, type in our mean, type in our standard deviation, and once again, that standard deviation came from this right here, from the bootstrap. And we can do our two-tail to get 95%, and then you can see down here, we have our 95% confidence interval. Now, remember we had said with the bootstrap distribution that the formula for doing a 95% confidence interval was our statistic plus and minus 2 times our standard error. And that works well, but if you're looking for a different confidence level, what are we going to do? Well, it's really that same formula, our statistic plus or minus, but it's not going to be 2. It's going to be something else times our standard error. And this z star, now the 2 remembered were 2 standard deviations above to 2 standard deviations below. This z star is how many standard deviations you are above or below for your desired specific confidence level. So if this is your confidence level here, Your z star would be how far you go on each side. So you can go ahead and figure out your confidence level. You put that in here, you get your z-score here in the bottom, and then that tells you how to be able to figure that confidence level or interval out with your statistics, the number you just got from stat key, and your standard error. So if we wanted to figure out the z-star for a 99% confidence level, we go to stat key. Towards the bottom, we click on normal distribution. We would want to do two-tail, and then we'd want to hit the middle, which comes up by default 0.95, and type in 0.99, hit enter, and then our z-star would be these two down here. In other words, it's 0.2577 for a 95% confidence interval. So if we wanted to do a 95% confidence interval for what we started off with the hearing loss, we would go ahead and take our mean, or not our mean, our proportion of 0.195 plus or minus this 0.2575, and that's the z star that came from our last slide for the 95 or 99% confidence level, times that standard error we had. And so when we take this and we add this here, we get this number up here. When we take this minus all this here, we get this down here. So that's our 99% confidence interval. Now, if you wanted to do a 90% confidence interval, you would go to normal distribution, hit stat, or on stat key, hit normal distribution, hit two-tail, and then it would come up as a 0.95. You hit that with your enter 0.9, and then it gives you your z-star on the bottom. Now, technically your z-star for a 95% is 1.96, but that's close enough to 2, so we approximate it with 2, but technically it's 1.96 for your 95% confidence level. So these are going to be the three z-stars that are going to be most common that you'll be dealing with. Your 95% confidence level z-star, your 99% confidence level z-star, and your z-star for 95%. So consider this. We have a proportion of 64% of the Americans use at least 3 different types of media every week. Standard error was 1%. We want a 90% confidence interval of the true proportion. So we would need to go our statistic of 0.64 plus and minus this 1.645 comes from our last slide for the z-star of 90% confidence level and our standard error of 0.10, because 1% as a decimal point is 0.01. So when we subtract this out, we get this here. When we add this together, we get this one up here. That's your 90% confidence interval. So are firstborn children smarter? So the explanatory is whether you're firstborn or not firstborn. The response would be the combined SAT score. So based on a sample of college students, we could take firstborn average or mean minus the not firstborn mean. When we do that, we get a 30.26. That's the difference, the mean difference between our firstborn and our non-firstborn on the SAT. If we do our randomization distribution, we get our standard error being 37. We could actually go ahead and use our normal distribution to get our p-values. We just need to know the area in the tails with our null value and our standard error for our normal distribution. So when we're looking at this, The normal distribution is assuming your null is true. So it centers it there. We have our observed statistic, which might be over here. Our p-value is the area that's from there and to the right, or if you had a lower level, less than, it would be from here and to the left. So if we look at this firstborn, remember our null hypothesis is assuming that there is no difference, so the difference between the two means would be 0. We had our standard error from that other slide being 37. On stat key, you can go ahead and do your normal distribution. You could go ahead and hit edit parameters, which would be over here. Type in 0, type in your standard deviation being 37. Do a right key, or not right key, right tail. And then remember our difference in our two means was 30.26. So you go down here, you click in the box that's underneath, type in 30.26, and it gives us our p-value right here.